To do any kind of motion control, we need Dragonframe to control some motors. The motors that Dragonframe wants to use are called stepper motors. They're a little bit more complicated to drive than a normal DC motor, and the reason for this is because in the case of Dragonframe, we want to do very precise control over the position of the camera at all times. And stepper motors are designed for that exact purpose. Instead of turning continuously while voltage is applied, the motor is designed to make very small steps, each step being 1/200th of a rotation. If you add gear reduction to it, you actually get very, very precise control over the position of the motor's shaft. Stepper motors come in lots of sizes, from itsy bitsy like this, NEMA 8 motor, to great big ones that would control industrial machinery. And it's just as easy to control a great big motor as it is an itsy bitsy one. Stepper motors are controlled by stepper motor drivers. Most industrial applications will use a big driver like this with lots of heat sink on it. You can use these for motion control rigs, but it's also possible to drive small motors with very tiny drivers like these. In principle, the little drivers work exactly like the big ones. This Allegro driver, the green one, is good for about 1 amp. The TI driver, the purple one, is good for quite a bit more than 1 amp. If you put a heat sink on it and a fan, you can drive up to 2 amps, which is probably sufficient for most small time-lapse motion control rigs, at least if you're moving nothing larger than a digital SLR. These drivers want to accept step and direction signal, and they have 4 output wires which go to the stepper motors. These particular drivers are for 4-wire bipolar stepper motors, and the motors they drive have 4 wires coming out of them. These drivers don't plug straight into your computer. They want to receive step and direction signals. Each time we want the motor to make 1 step or 1/200th of a revolution. So if we wanted the motor to turn completely around once and come back to its starting point, we would have to give it 200 steps to the motor driver. The other signal is a direction signal, and when it's high, the motor turns in one direction. When it's low, the motor turns in the other direction. You don't send voltage straight to the motor. You have this little circuit in between the motor and your battery. So we need to get step and direction signals into our stepper motor drivers. And there are lots of breakout devices for Dragonframe. The one I'm going to show you today is our miniDF. It plugs into your computer with the USB plug, and it has 4 motor ports. Each of the motor ports supplies a ground and step and direction signals which go to your motor driver. So at this point you can kind of see how this works, and that it's not going to be all that complicated anyway. These motor ports have a tip ring sleeve type plug. So 3 connections are made when you plug the plug into the socket. At the other end of this cable are 3 wires: the common ground wire, the step wire, and the direction wire. And there are places on the driver for attaching these wires. I've got my stepper driver. I've got my tip ring sleeve cable that plugs into the miniDF. And I've got some insulation stripped off the other end. And just a tiny bit, maybe 3/8 of an inch of bare wire at the end of the 3 conductors. I have a barrel plug for 12 volts and the positive and negative wires similarly with about 3/8 of an inch of insulation stripped off the end. And I have my stepper motor with the 4 wires coming out of it. And since I've looked it up on the website from the guys that sold me the motor, I know that black and green represent one coil and red and blue represent the other coil. So now I'm ready to start wiring the driver. I also have one additional short piece of wire, and now I'm going to zoom in on the connection block of my driver so that you can see it better. These screw terminals make it real easy to connect your wires, and which wire goes where is written on the top of the driver. So we'll start at this end. This says DC plus, DC minus. So this I'm going to connect to 12 volts from my barrel plug. And so it's very simple. DC plus goes into the one marked DC plus, and you tighten down the screw. Make sure it has a firm grip on the wire. And the negative side from the battery goes into DC minus. And we'll tighten that down. So now I've connected power to my driver. Now I'll connect the motor. Using the information that I got about the color coding of the wires. The first coil can be the black and green one. Okay, and the other coil is red, then blue. So there's all my wires for the motor and for supplying power to the driver. Now I'm going to connect the wires from my tip ring sleeve plug to the direction, and in this case pulse. Pulse means the same thing as step. Now this particular driver has a connection for direction plus and direction minus. The direction minus is the ground for direction. It also has connections for pulse plus and pulse minus. And of course, pulse minus is the ground for the pulse signal. My 3 wires here are pulse, direction, and ground. And what I'm going to do with the extra wire is I'm going to connect it to my ground wire and create a little jumper that will jumper the ground signal to the other input. So I'll start here with direction ground. I'm going to jumper over here to the pulse ground. And now I can connect my direction plus. And this one gets connected to pulse, our step signal. So there it is. I now have battery, motor connections, my pulse, my direction signal, and the grounds for pulse and direction are jumpered to each other. And I should be all set. The other thing that I'm going to need to set is the current, and if desired, the micro-stepping. Here are the dip switches which control the current and the micro-stepping mode of this driver. There's a little lettering right here at the bottom. It indicates on is down. On the top of the driver are graphs that show me how to set the micro switches. I want to set 0.06 amp micro stepping, which is switch 1 off, switches 2 and 3 on being down. So switch 1 is already off. I'll set switches 2 and 3 to on. I also want full steps, so I don't want micro stepping engaged, and the same code applies for full steps. Switch 4 is off, 5 and 6 is on. If I wanted micro stepping, I would set these to a different value, just depending on what micro stepping mode I wanted. So I'm plugged into my 12-volt battery, and since there's no power, the motor turns freely. I'm going to turn on my battery, and the motor won't turn. That's because the driver is sending current to the motor to hold its position. So far so good. Here's everything all put together. I've got Dragonframe running on the laptop. I'm in the arc motion control window. I've got my miniDF plugged into the USB port. I've got the tip ring sleeve plug plugged into the miniDF, and that is wired into step and direction signal input on my driver. The 4 wires from the motor are connected to the driver, and 12 volts from this battery is connected to the driver. The motor won't turn. It's holding position because the battery is on, the driver is on. It's connected to motor port 1, which I have assigned as dolly. And there we go. The motor is turning. Now all I need to do is the mechanicals to get the motor to actually move the dolly. Drivers like this work very well, and they can drive very large motors. This particular one is for just 12 volts from 0.2 amps up to 5 amps. Drivers of this type are available in much higher voltages and capable of driving much higher currents. So if you want really huge motors, you can definitely get drivers in this style package to run them. Now, most DSLR rigs don't require huge motors. This is a stepper motor driver. It uses an Allegro driver chip, and it can drive up to 1 amp motors. This Texas Instruments driver is the same size package, and most of the pin configurations are compatible between these 2 drivers. This one is better for driving very high currents. Can drive 1.5 amp motors without any additional cooling. It can drive upwards of 2 amps given heat sinks and fans. I've gone to the pololu.com website to look up how to connect my stepper motor to the driver. First thing I did was look up my stepper motor, and in amongst all the other data for it, it shows this wiring diagram that tells me which colored wire goes to which lead on the motor. We can see that there's 2 coils on the motor, and this coil here has a connection called A and C, this lower coil B and D, and that these are represented by the blue wire to A, the green wire to C, the red wire to B, the blue wire to D. Now, you would think that I could just look up my stepper motor driver and it would be clear how to wire the motor. This is the wiring diagram, the minimal wiring required to make the TI drivers run. This will be the same for either the low current or the high current TI drivers. Here we can see the motor has 4 wires connected here, and the outputs on the board are labeled B2, B1, A1, and A2. How these are supposed to connect to A, B, C, and D on the motor is not very clear. Although if I read on some more here, I will find in the frequently asked questions, they specifically tell me how to wire the motor. Connect stepper lead A to output A1. stepper lead C to board output A2, stepper lead B to output B1, and D goes to B2. So I've made a little cheat sheet. Here's my motor diagram. The two coils, A, C, B, D. The color coding of the wires, A being black, C green, B red, D blue. And the connections for the TI driver. A1 being black, A2 green, B1 red, B2 blue. And here I have the outputs lined up the way they are on the driver itself. So if we have the outputs on the right side of the driver and we're looking down on it from above, B2 is the blue wire, B1 the red wire, A1 the black wire, A2 the green wire. And this is the information we really need to know. Blue, red, black, green. Back to the wiring diagram for the driver. We now know how to connect the 4 wires for the motor. These 2 wires above it are labeled V-mode and ground. This is where you attach your 12-volt battery that would run the stepper motors. V-mode, the topmost connection, is positive on the 12-volt battery, and ground, the next one down, is the negative battery terminal. This particular driver needs a 100 microfarad capacitor across these 2 connections, that is between where the positive battery connection and the negative battery connection are made. And this capacitor should be as close as possible physically to this board. Don't put the capacitor way back at the battery. Put it wherever you're connecting your wires from the battery. The other connections required to make it go are step and direction and a common ground between that references the step and direction signals. A 0 is ground potential, and a 1 on these logic inputs for step and direction is 5 volts. This driver also requires anywhere from 2.5 to 5.25 volts to be applied to these 2 pins. Reset and sleep. On the diagram it shows these with a bar above them, which means not. The logic bits for these inputs are reversed. That is, no voltage here. A 0 means reset, and a 1 means don't reset. Resetting the chip would prevent the motor from turning. Also, putting the chip into sleep mode also would prevent the motor from turning. And these would be activated whenever there's no voltage at these pins. So, because of the way they use the negative logic here, we need to apply 5 volts to these 2 pins continuously for the driver to run. And those are the only connections to this driver. Basically, everything is run off of the 12-volt battery that runs the motor, except these 2 pins. And I could use a separate 5-volt power supply for these if I'm using a microcontroller or some other means to send step and directions to the stepper motor driver, I can use the power supply from the micro to set these pins high. Some batteries have multiple voltages at their outputs, and so I can get 12 volts, and I can also get 5 volts from the same battery. I can wire the ground from the 5 volts to this pin here, and I can wire the positive 5 volts from the battery to these two pins here. I'll also connect the ground from my miniDF to this pin as well, so that the step and direction signals from my miniDF are reference to that ground potential. So those are the wires. Very simply, your 12 volt battery, your negative terminal from the 12 volt battery. You need to have a 100 microfarad or more capacitor across there. The 4 motor connections that we now know how to do. The ground, step, and direction signals. And these 2 pins here that we need to keep high. That's all we need to wire to make the motor go. To simplify my life, since I'm going to be connecting several motor drivers, I'm going to use a different driver for one of the motors, and I'll show you why. This driver from Pololu has a built-in voltage regulator. Actually, it has 2 regulated voltages, 3.3 volts and 5 volts. And normally this is very convenient if you're going to be using a microcontroller to create your step and direction signals. This 5 volts can also power your micro. This 5 volts also can power logic circuitry on the board itself. And this can be done at 3.3 volts or 5 volts depending on the voltage that you use for your micro. Today we're going to be using 5 volts because that's compatible with the miniDF. And the 5 volt output from the voltage regulator is this second pin up here, the second connection, and we can just jumper it to the next pin down called VDD, and it will supply power to all the logic on this board. We'll also take a wire from the 5 volts and we'll run it over to our other stepper motor drivers in order to keep reset and sleep high. This is a convenient way of doing it so that I don't have to wire a voltage regulator and another capacitor on my circuit board, but I could definitely put in a voltage regulator and get my 5 volts from there. Just to make things interesting, let's take a look at the output connections here. Remember, our TI driver has 4 outputs here in a row like this, labeled B2, B1, A1, and A2. The Allegro driver has 4 connections labeled 2B, 2A, 1A, 1B. I go to the frequently asked questions and see how to wire my stepper motor. In this case, lead A goes to output 1A, C to 1B, lead B to 2A, lead D to 2B. Lead A from the motor being the black wire, C being the green wire, B being the red wire, D being the blue wire. I've made the conversion from the instructions in the frequently asked questions for the Allegro driver, and I've also arranged the outputs the way they are physically on the driver. 2B is connected to D, the blue wire, 2A to B, the red wire, 1A to A, the black wire, 1B to C, the green wire. You really can ignore the names of the outputs. B2 is 2B, B1 is 2A, A1 is 1A, and A2 is 1B. But the significant thing is that if you have your motor outputs on the right side of the driver board and you're looking down from above, the order of the wires is always the same. Blue, red, black, green. Blue, red, black, green. So the connections coming out of the board are the same, and in many respects these drivers are interchangeable. After all the confusing naming of wires and connections not matching, the thing you need to know is blue, red, black, green. I should have started with that. Different motors may have different colored leads coming out of them, and even if they have these colors, they aren't necessarily going to be in this order. But the place where you buy the motor will somehow have information available that looks like this. A diagram, a circle with an M in it representing the motor. The two coils will always be represented like this, and the corresponding locations, however they're labeled, will go to the same locations that we have here. And you know which goes to which coil and which is the first and second part of each coil. So if you keep your little cheat sheet like this, you'll be able to convert this information in order to wire your driver. A quick and easy way to set up your drivers or prototype any kind of electronic circuits is with these wireless breadboards. Pretty much all of your wiring without having to solder. The little holes are wired together along the rows this way. And then there's a strip in the middle with no conductors, and then of course the rows on the other side. This particular breadboard has rows connected along the edges this way for conducting power or any kind of signal that you want to run as a bus along the length of the board. Components like this stepper driver with headers on it. Plug right into the board like that. So this pin here is connected to these three holes going across here. This next pin is connected to the adjacent three holes. And I can make connections between this and other parts of the circuit by just sticking, I have a piece of wire with a little bit of the insulation stripped off the end. I stick that in the hole, and it's now connected to this end pin on the stepper motor driver. I can stick the other end of it in this hole, and it's now electrically connected to everything in that row. So I can stick another component here which would be connected to this pin by this wire. Here's a wireless breadboard, and it's already got the stepper motor driver with the voltage regulator on it. I don't know how easy it is to see, but I've got a jumper going from the regulated 5-volt output to where the board wants its logic voltage, 5 volts. I've also got a jumper going from there to this red line that goes the length of the board. I've got jumpers here to continue that. I've also jumpered across to the other side of the board where I've got the 5 volts running along the red line. I've also got this 5 volt pin here connected to the red. So that's basically connecting these 2 pins. And the ground from this board is connected to the blue line, which again is connected all the way around the edge. So I've got ground and 5 volts on these lines all up and down the board. So I can plug more stepper motor drivers in along here and connect up the 5 volts from this voltage regulator to supply the 5 volts for all of my stepper drivers. There really isn't a whole lot that I need to connect to this. The 4 pins going up from here are the motor. I have the 4 motor wires connected to a plug, and that goes right in there. That connects my motor wires. I have my barrel plug for 12 volts, and it goes in the next 2 sets of holes. I'm going to make sure that I get the positive out at the end and the ground is adjacent to the motor wires. And there, I've now wired the motor and power. The only other connections I need come from the miniDF Dragonframe controller is ground, step, and direction. And I'm going to put ground also connected to this end pin, which is a ground pin for the stepper driver. Red is probably not the best choice of color for ground. The direction signal goes to the pin at the very end here. In my case is the white wire. My green wire is the step signal, which will go plugged in the board so it connects to the next pin over. And those are all the connections I need to plug into Dragonframe and make the motor turn. I have Dragonframe running. I'm in the Arc Motion Control window. I've got my miniDF plugged into the USB port on the computer. I've got my stepper motor driver plugged into motor port 1 on the miniDF. My motor's plugged in, my battery's plugged in. At the moment, the motor turns freely. I'll power it up. Now the motor is locked in position because the driver is applying current for the motor to hold position. And since I've assigned motor port 1 to be the dolly, I can now move here and jog the motor. I'm going to temporarily remove a few of the input wires. And I'm going to start wiring up the next driver. The motor wires are facing the same way as the other one. That should just make things a little bit less confusing. So at the moment, I've removed my motor wires, my step and direction wires from this driver, but I still have my 12 volt plug to the battery attached here. And I'm going to start wiring this driver. And since I already have 5 volts available to me, this is going to be very easy to do. I've got some little pieces of wire with the insulation stripped off a little bit at the end. And like everything else, these stick right in the sockets here. I've just stuck this end of the red wire in where positive 12 volts is. And looking at the web page that shows the wiring diagram of this, I see that wants to be attached. 12 volts motor voltage is the very end pin on the stepper driver. So I'll plug the other end of this wire into one of the holes in the row corresponding to the end pin. The ground wire, or the negative side of the 12 volt battery, gets wired to the very next pin on the stepper driver. So again, I'm going to use a little piece of wire as a jumper and connect from negative 12 volts there. So now I have my 12 volts connected up to this driver. Now remember, the TI driver needs a 100 microfarad capacitor across the 12 volt input. It's a 100 microfarad electrolytic capacitor, and it has a negative wire and a positive wire. And which one is which is usually marked on the outside of it like this. And so I'm just going to get the negative side of that. And that takes care of that. Now, remember, there were 2 inputs to this driver that needed 5 volts to enable the driver to run. And they were the 3rd and 4th pin up from the end on this side. Now I'm not going to connect them to this red wire that I just jumpered from over here, because that's 12 volts and that would fry my driver. But I've connected my 5 volts from this, the regulator on this driver, to these rails along the side of the board. So what I can do is make a jumper from the positive 5 volt rail, and I'm going to put it over by the 4th on a row parallel with the 4th pin on the driver, which is the reset pin. And holding this high will prevent the board from continuously resetting itself. The next pin over the third pin also wants to see the 5 volts, the sleep input. And so I've got another little piece of wire that I'm jumpering over to there. So I've now brought 5 volts from the regulator here to reset and sleep. My other connections are from the miniDF, and I'm using the same wires as before, with red being an unfortunate choice for ground. White is direction, which goes to the very end pin on this side, and my green is the signal for step, which goes in the pin right next to it. So along this side, starting at the end, I have white direction, green step. The next pin is the jumper for 5 volts over to the next adjacent pin, and that pin over to the 5 volts. And the only 4 additional wires that I need to connect are my motor wires, which are wired in the same physical order on the TI as the Allegro. So this end pin is ground from my miniDF. The next pin needs no connection, and my 4 motor wires start with the third pin from the end. There. My motor is connected. I could plug another motor into this driver, and I would have 2 motors wired up. At the moment, I'm just going to test the connections to this second driver. So I'm using the same motor as before. Here's my solderless breadboard with the TI driver hooked up to the motor, and we're using the 5 volts from this Allegro driver from Pololu, and my miniDF. I'll turn on power to the drivers. The motor is being held in position, and now once again in the ARC Moco window, and there we go. I can move my motor. I can use this 5 volt regulator to power several more TI drivers. With this little battery, I'm not going to be able to supply enough juice to run all the motors. So the only change that I would make, if I want to continue using these batteries, would be to hook up a separate 12 volt source to each of the TI drivers down the line. The other option is they can be wired daisy chain style this way, but you'll need a battery capable of putting out more amps if you're going to drive very significant motors. Each of these drivers has a current adjustment, and before running the motors a lot, or even leaving the power turned on for any length of time, it's best to adjust that. The Allegro driver has it here. It's this little tiny adjustable resistor. The TI driver has one right here. That little resistor there. So what I'm going to do now is run the motor some. This is with what is a good adjustment. I'm going to turn it all the way down again. So this does not have enough current to turn the motor. Just a little bit of current and the motor stutters, missing most steps. A little more current. There it is. But you can see it's stuttering. It runs smooth at high speed, but that's stuttering at very low speeds as it goes through resonance. So I'm giving it a little bit more. That's good, but I can see a little jittering still as it goes through resonance. So a little bit more. That's almost got it. So this will be my preliminary current setting, and if I apply some resistance to turning, what happens? It's running pretty smooth, so I'm going to leave it like that for now. It might need some fine tuning once I've got some load on it, but that's the current adjustment. There's other ways to do it. Another way of doing the current adjustment would be to cut one of these motor wires and insert an amp meter in the line, and without running the motor, measure the current going through the wire. And you'll need a meter with a fairly high current setting, or you'll blow the fuse in your meter. The driver will normally set 70% of current to hold position on the motor. And so you take the maximum current that your motor should be given, you multiply by 0.7, or take 70% of that value, and you adjust the trimmer until you see that amount of current in the meter where you've cut into the wire. You should never connect or disconnect the wires while power is onto the driver. If you do that, you'll fry the bridge in the driver chip and it won't work anymore. Always disconnect power before connecting or disconnecting any of the motor wires.